Let's look at sulfur dioxide, another example, and again let's add up the electrons. 6 for sulfur. We have 2 oxygens, 6 each. That gives us 12 from the oxygens for a total of 18. I'm going to make sulfur my central atom because it has the highest valence. It can make the most bonds. Remember that sulfur is right underneath oxygen in the periodic table. So it will have bonding patterns similar to oxygen, but it's going to have additional bonding patterns as well. Because remember that sulfur, being a third row element, can expand its valence shell. So I might start with something that looks like this, and if I count up my electrons, you'll see I only have 16 electrons. I need to add in a pair of electrons here somewhere. And I also would notice that the sulfur does not have its valence satisfied. There's only 4 electrons in its valence shell, so let's give that extra pair of electrons to the sulfur. And now I have 18 electrons in this arrangement, but I've not yet satisfied the valence of sulfur. So one thing that you can do when you've got all of your electrons in the structure that you're trying to make and you still haven't satisfied the valence of each atom, look at your lone pairs and see if you can start making double bonds. So if I move that lone pair of electrons in and make a double bond between the oxygen and the sulfur, now you'll see that sulfur has an octet of electrons. That sulfur is happy. And I can calculate my formal charge for each of these atoms. Sulfur would be 6 minus 5. Oxygen 6 minus 6. That's my oxygen on the left. All right. And oxygen on the right would be 6 minus 7 for a minus 1. All right, so let's put in the charges. We have a positive charge on sulfur and a negative charge on oxygen. Now this structure is not so bad, except for the fact that I have separation of charge on 2 atoms that are bonded to each other. Whenever you see this in a Lewis dot structure that you're trying to generate, trying to draw, one thing that you can do is, again, move one of those lone pairs of electrons in from the negatively charged atom towards the positively charged atom to make another double bond. Now I come up with a structure that looks like this. Each of my oxygens is identical and each has 8 electrons in its valence shell. But look at my sulfur. It has 10 electrons in the valence shell. But that's okay, because remember, sulfur is a third row element, and sulfur can expand its valence shell. And now if I calculate my formal charge, for sulfur, for instance, I start with 6, and I'm going to assign 6 electrons to that valence shell. I have 1, 2, 3, 4 bonds, right, for 4 electrons, plus 2 more is 6. So sulfur has a charge of 0. Oxygen has 2 bonds for 2 electrons plus 2 lone pairs for 4 electrons. So it's going to be 6 minus 6 or 0. So now I have a Lewis dot structure in which I have no formal charges on any of my atoms. My oxygens have an octet. My sulfur has more than an octet, has 10 electrons in its valence shell, but that's okay. Let's look at ozone. Again, let's add up the electrons. We have 3 oxygens, so 3 times 6 is 18. I have a total of 18 electrons in the molecule of ozone. Now, you'll notice, or you may recall, that we had 18 electrons in our SO2, our sulfur dioxide. And you might come up with a structure that looks like this. So we have the same arrangement of electrons that we had for SO2. But the problem with this is that I have 10 electrons in the valence shell of the central oxygen. And that's not good. Oxygen is only a second row element. It cannot accept more than 8 electrons. So I'm going to have to move out one of those bonding pairs of electrons and give it to an adjacent oxygen. Now I have a structure that looks like this one. I have 3 unique oxygens, so I'm going to have to calculate formal charge on each of them separately. For oxygen 1, we start with 6 electrons in the valence shell, and we assign 7. We have 3 lone pairs for 6 electrons and 1 bond for 1 more electron, so that's 6 minus 7 or minus 1. My central oxygen, oxygen number 2, starts with 6, and I assign 5 because I have 3 bonds for 3, a lone pair of electrons for 2 more, so that's a total of 5. 6 minus 5 is 1. Oxygen number 3 again starts with 6 in the valence shell minus the number that I'm going to assign to that oxygen, which is 4 for the 2 lone pairs plus 2 more for the 2 bonds, so this becomes 6 minus 6 or 0. Overall, my charge for ozone is 0, or ozone is neutral, and this would be the correct Lewis dot structure for the molecule ozone. Remember that we could not arrange the electrons in the same way that we arrange them for SO2 because oxygen cannot accept more than 8 electrons in its valence shell. Now I want to point out to you that there are some additional acceptable Lewis dot structures for the formulas O3 and SO2, and I'm showing those to you here. If you count the electrons in each of these structures, you'll come up with 18 electrons. Each of the atoms has their valence satisfied, or their octet satisfied. So these are perfectly acceptable Lewis dot structures. The only problem is that they're not the correct structure for the molecules. And as I mentioned earlier, as you come across more and more complex molecules, there are more and more possibilities for putting them together or arranging those atoms and those electrons. Sometimes those possibilities will represent a real molecule, and sometimes they don't, and in this case, they do not. However, if I gave you a question and I asked you to draw for me the Lewis dot structure for ozone, O3, and you came up with this structure on the left, I would have to give you credit for that, unless I said to you, ozone is not a cyclic molecule, or ozone is going to be linear. All right, so sometimes I might give you some hints to guide you towards the correct Lewis dot structure. So I want to show you just another way to look at how to calculate formal charge, and this might be a little bit simpler than what we've been doing. And what you want to do is to draw a circle around each atom, and when you draw that circle, you want to include the non-bonding pairs that are assigned to that atom, and cut the bonding pairs of electrons in half. Then what you're going to do is count the number of electrons inside that circle. So in this case, for this oxygen on the right, I have 6. I have 4 non-bonding electrons, and I have 2 bonding electrons that I'm going to assign to that oxygen. Same thing for the oxygen on the left. It's identical to the one on the right, so I'm going to assign 6 electrons to that oxygen. For the sulfur, I have 4 bonds. 1 electron from each of those 4 bonds I assign to sulfur, so that's 4, plus the non-bonding is 2 more, so that's a total of 6. So now when you calculate formal charge, again, you subtract the number of electrons assigned to the atom in the molecular ion from the number in the neutral free atom. In each of these examples up above, it's going to be 6 minus 6, or 0. So in our earlier video where we talked about common bonding patterns or normal bonding patterns, what those really represented was for second row elements that had no charge. Second row elements when the atom was neutral. And I told you that that's what you're going to be coming across most of the time in this course, but sometimes you're going to see some atoms that are charged. These are often reaction intermediates that are short-lived, but they're really important in terms of understanding reaction mechanisms, and we'll get to that later on in the semester. But I want to call your attention to some of these more common structures that we'll come across throughout this class where the atoms do have a formal charge. So for carbon, Carbon can either have a positive charge or a negative charge. So for my positive charge, I'm going to calculate the formal charge in exactly the same way that we've been doing. I have 4 electrons in the neutral free atom. I get that number from the periodic table. I have 3 bonds. 4 minus 3 is a charge of 1. For this carbon with the negative charge, again, I'm going to assign now 5 electrons because I have 3 bonds plus 2 electrons from a lone pair. So this 5 represents the 3 bonds plus 2 electrons from the lone pair. For nitrogen, remember we start with 5. If nitrogen has 4 bonds, I subtract 4 electrons for a formal charge of 1. In this next example, you can see nitrogen has a negative formal charge. So I start with 5, and this number 6 arises because I have 2 bonds, so that's 2 electrons. 2 lone pairs gives me 4, so that's 2 plus 4 is 6. 5 minus 6, negative 1. For my positively charged oxygen, I start with 6, I subtract 5. 5 because I have 3 bonds and 2 non-bonding electrons. So that's 3 plus 2 is 5. That gives me a formal charge of 1. Here I'm going to assign 7 electrons to this oxygen. I have 3 lone pairs for 6 plus 1 bond gives me a total of 7. For the halogens, again, I'm going to assign 6 electrons to that halogen. And by the way, we often use an X to represent halogens, just in general, to represent that whole family. So I have 2 bonds, or 2 electrons, plus 2 lone pairs for 4 more electrons, a total of 6 that I assign to that X. 7 minus 6 is 1. Now, I just want to point out something to you about a different kind of covalent bond. We've been talking about covalent bonds where you have each atom contributing 1 electron to form that bond. Well, remember we talked about boron and how boron can form only 3 bonds because it only has 3 electrons to donate to a bond. So even in this neutral state, this neutral molecule of borane, BH3, that I'm showing you on the right, boron is electron deficient. And I told you that if boron wanted to have an octet, it would have to get a pair of electrons from someone, some other atom or element or molecule that was willing to donate it. And boron can accept that non-bonding pair or lone pair of electrons from nitrogen in NH3 or ammonia. And it can form a complex, and that new bond where nitrogen contributes both of the electrons to the bond, we call that a coordinate covalent bond. And let me just draw that in with a dash to represent the bond. And if I were to calculate the formal charge, remember that nitrogen has, with 4 bonds, is going to have a formal charge of +1. And let's go ahead and calculate the formal charge for our boron. We start with 3 in the neutral free atom. We get that number from the periodic table. Since I have 4 bonds, I'm going to assign 4 electrons. So I have 3 minus 4, or -1 charge. Believe it or not, this is an acid-base reaction. It's a little bit different kind of acid than what you have studied in general chemistry. We call this a Lewis acid on the right, BH3, borane, because it's electron deficient. A Lewis base on the left. So this is really an acid-base reaction. We're going to talk about this in a little bit more detail. Well, in a lot more detail, actually, in Chapter 3, but I just wanted to give you a little heads up about that. So there you have formal charge, Lewis dot structures, and coordinate covalent bonds.